Right now, a headline is racing across social media claiming the James Webb Space Telescope just captured the first real image of another world. It has already been shared hundreds of thousands of times. No planet outside our solar system has ever been photographed exactly the way that headline describes. No one sharing it seems to know what Webb actually did earlier this year, something no telescope has ever managed before, on any world, at any distance. It is not a hoax exactly. It is a real breakthrough wearing the wrong headline. Stay with me, because by the end of this, you will know precisely what happened and why the scientists behind it described this result in 4 blunt words: a dark, hot, barren rock. This channel exists to separate real discoveries from viral noise, one mission at a time. If that sounds useful, the subscribe button is right there. Let us go back to the beginning. To understand why that viral claim is wrong, you first need to understand just how hard it actually is to photograph a planet around another star, and why almost nobody has ever managed it. Nearly 6,000 exoplanets have been confirmed since the 1990s, and the overwhelming majority were never seen directly at all. They were inferred, caught by the tiny dimming of a star's light as a planet passed in front of it, or by the faint gravitational wobble a planet induces in its star. That approach was reasonable because it worked, because the alternative is genuinely brutal physics. A star can be 10,000 times brighter than the planet orbiting it, sometimes far more, which means trying to photograph the planet directly is like trying to photograph a firefly hovering a few feet from a lighthouse beam from miles away through fog. For most of the exoplanet era, that fog simply won it every time. Those indirect methods were not a shortcut born of laziness. They were and still are extraordinarily precise tools. The transit method can detect a dimming in starlight of a fraction of 1%, precise enough to infer a planet's size just from the shadow it briefly casts. The radial velocity method can detect a star wobbling at walking pace, tugged almost imperceptibly by the gravity of something orbiting it. Both techniques built the modern field of exoplanet science, essentially from nothing, and both remain the backbone of how the vast majority of the 6,000 known exoplanets were actually found. But neither one gives you a picture. Neither one tells you what color a planet is, what it's made of, or what, if anything, might be happening on its surface. For that, astronomers needed something built specifically to fight through the glare rather than work around it. The James Webb Space Telescope, launched on December 25, 2021, and fully operational since the summer of 2022, was built with instruments specifically designed to cut through that glare. Coronagraphs, small internal masks that block a star's light so instruments can pick out anything faint hiding nearby. On September 1, 2022, astronomers used those coronagraphs to capture Webb's actual first direct image of a world beyond our solar system, a young gas giant called HIP 65426b, roughly 6 to 12 times the mass of Jupiter, orbiting a star nearly 400 light-years away, sitting far enough from its star, about 100 times the Earth-Sun distance, that Webb could finally pull the two apart in a single frame. That was the real first. It happened in 2022. Remember that date? Because it is the number every viral claim about a brand new first image is quietly and incorrectly competing against. Since then, Webb has photographed a small but growing handful of exoplanets directly, almost all of them, like EAPS 65426b, enormous, young, glowing gas giants, easy targets, relatively speaking, because they are still warm from their own formation and radiate enough infrared light to stand out. What Webb had never done until this year was something considerably harder. Use its instruments not to photograph a small, cold, rocky world, but to directly read the surface material of one, to determine from 49 light-years away what kind of rock a distant planet is actually made of. That target had a name already sitting in the astronomical catalog since 2019, LHS 3844b, a so-called super-Earth, roughly 30% larger than our own planet, orbiting a small, cool, red dwarf star in just 11 hours. Now hold that number for a second. 11 hours, not days, is a full year on that world. It orbits so close and so fast that gravity has permanently locked one face toward its star and the other into total darkness forever. Here is the finding, in the plainest terms astronomers themselves used. Earlier this year, Webb detected light coming directly off the baked, sunlit surface of LHS 3844b and used it to determine, for the first time on any exoplanet, what that surface is actually made of. Read that again, not the planet's atmosphere, which is what nearly every previous Webb exoplanet study had focused on, but its bare geological surface, 49 light-years from Earth. Translate the temperature to something you can actually feel. The sunlit side of LHS 3844b sits at roughly 1,240 degrees Fahrenheit, 725 degrees Celsius, hot enough to melt lead, hot enough to glow faintly on its own, a temperature more associated with lava flows than with anything resembling a planetary surface as we understand the word. The technique itself is almost deceptively simple to describe, even though executing it is anything but. As LHS 3844b orbits its star every 11 hours, it periodically passes directly behind it, an event astronomers call a secondary eclipse. In the moments just before that happens, the telescope is picking up combined light from both the star and the blazing hot day side of the planet. The instant the planet slips fully behind the star, that combined light drops by a small, precise amount, exactly the amount the planet itself was contributing. Subtract one measurement from the other, and what's left is the planet's own thermal glow, isolated and pure, with the star's overwhelming brightness subtracted out of the equation entirely. It is less like photographing the planet directly and more like weighing an object by first weighing yourself holding it, then weighing yourself alone, and trusting the difference. Using Webb's mid-infrared instrument, a research team led by Laura Kreidberg of the Max Planck Institute for Astronomy and Sebastian Ziba of the Center for Astrophysics at Harvard and Smithsonian observed the planet slip behind its star 3 separate times between 2023 and 2024, measuring the faint infrared glow radiating off its day side each time it briefly vanished and reappeared. Then came the delayed reveal. They took that spectrum of light and matched it against the known infrared signatures of real rock and mineral samples from Earth, the Moon, and Mars, the same kind of comparison a geologist might run on a sample brought back in a rover's collection tube. What most people are not seeing when this story gets summarized online is that this comparison actually ruled something out first. An Earth-like crust rich in silica and granite, the kind of rock that forms only through water-driven geology and plate tectonics, slowly recycling material over billions of years, was not a match. This is not a world with continents. It is not a world with oceans that ever were. What matched instead was basalt, a dark, dense iron and magnesium-rich volcanic rock, the same material that makes up much of the Moon's surface and most of Mercury's. According to the team's published findings, LHS 3844b appears to be a dark, hot, barren rock. Stripped of any meaningful atmosphere, its entire day side a lightless, airless expanse of dark, volcanic stone under a red dwarf sun. This is not the first photograph of an exoplanet. It is the first time astronomers have used a telescope to directly determine what an alien world's surface is actually built from without ever landing a single instrument on it. Here is where this stops being abstract and starts mattering to a question every single one of us has, whether we've articulated it or not. Are we alone? The entire long-term ambition behind exoplanet science, the reason billions of dollars and 40 years of engineering have gone into telescopes like this one, is not just to find planets, but eventually to determine which of them could actually support life, and that determination hinges on exactly this kind of surface and atmosphere characterization. LHS 3844. B itself is almost certainly too hot, too close to its star, and too airless to host anything alive. But the technique used to reach that conclusion, reading a planet's composition from its own thermal glow at 49 light-years without a single spacecraft ever leaving our solar system, is the same technique astronomers will eventually turn on smaller, cooler, more Earth-like worlds. This result is not the discovery of life, it is proof the method for finding it actually works. Think about what that means practically. Every single future headline claiming astronomers have found a second Earth is going to rest on exactly this kind of measurement. Faint light, subtracted starlight, a spectrum compared against known materials, long before anyone ever produces an actual photograph worth looking at. LHS 3844b is the proof of concept nobody asked for by name, a rehearsal for the moment, likely still years away, when this same technique gets pointed at a planet small enough, cool enough, and far enough from its star to actually matter for that question. Getting there was never guaranteed, and the honest story of how this measurement happened is a story of a result that could easily have collapsed into noise. LHS 3844. B first drew scientific attention back in 2019 when it was discovered by NASA's TESS mission and immediately flagged as a priority target, because rocky planets locked in tight, blistering orbits around red dwarf stars raise one of the more contested questions in modern exoplanet science. Does stellar radiation strip these worlds of their atmospheres entirely, or can some of them hold onto a thin envelope of air? Kreidberg's team went looking for an answer that same year using the aging Spitzer Space Telescope and came back with a result that unsettled as much as it clarified. No evidence of a thick atmosphere at all, a planet that looked from a distance essentially naked. But Spitzer's instruments were not sensitive enough, and its data not precise enough, to say anything about what was actually sitting on the ground. The planet became a known unknown, filed away, waiting for something better. Think about what that actually meant for the team picking this project back up years later. They weren't starting from a blank slate with a promising target. They were starting from an earlier published null result. A real chance that the entire follow-up campaign would simply confirm, in slightly more detail, that there was nothing here worth the telescope time at all. That risk doesn't show up in a press release, but it shapes every decision a research team makes before committing years of a flagship telescope's limited schedule to a single small, hot, unglamorous rock. That something better did not arrive quickly or easily. Directly measuring surface composition from 49 light-years away means isolating a signal that is, by the study's own numbers, thousands of times fainter than the star it orbits. A whisper riding on top of a scream. A single observation would not be enough to trust. Instrument noise, tiny calibration drift, or a fluke in the data could each masquerade as a real signal and send the whole conclusion in the wrong direction. So the team built the case slowly, deliberately, watching the planet vanish behind its star and reappear 3 separate times across 2023 and 2024, each secondary eclipse adding another layer of confirmation rather than resting the entire finding on a single fragile measurement. Here's where it gets worse before it resolves. One of the 2 most exciting possible explanations for what they were seeing, a young, geologically active surface, resurfaced recently by fresh lava, carries a very specific, testable prediction. Active volcanism releases gases, sulfur dioxide chief among them, and if that gas were present in any meaningful quantity, Webb's instrument should have caught it. The team looked specifically for that signature, and found nothing. Not a trace. That single null result didn't kill the volcanic explanation outright, but it complicated it enormously, forcing the team to sit with genuine uncertainty rather than declare an easy, satisfying answer. That tension, a result confirmed but its underlying cause still contested, is exactly where the study stood when it was finally published, and exactly where the deeper mystery of this planet remains today. Had the team stopped after a single eclipse, or accepted the first ambiguous reading rather than pushing for 2 more across an entire additional year, the finding likely never would have survived peer review at all. The difference between a headline-worthy discovery and a discarded false alarm, in this case, was a research team's willingness to keep watching a planet vanish and reappear behind its star 3 separate times before trusting what they were seeing. Here is what is happening right now, in 2026. The Ziba and Kreidberg team's findings on LHS 3844-I were formally published on May 4, 2026, in the journal Nature Astronomy, capping roughly 2 years of eclipse observations and analysis. It landed in the middle of what has become an unusually dense stretch of exoplanet headlines from the same telescope. In March, a separate team reported a strange sulfur-rich world called L 98 to 59d, 35 light-years out. Weeks after that, a rocky planet once thought too small and too battered to hold any atmosphere. TOI 561b turned out to have one after all. By July, Webb had found an entirely unexpected giant planet hiding inside one of the most photographed and heavily studied star systems in modern astronomy. Webb itself, meanwhile, quietly passed its 4th full year of science operations this past summer, still functioning at essentially full capacity, still returning data that keeps rewriting assumptions astronomers considered settled only a few years ago. In the same stretch of months, the telescope has also turned up an unexplained molecule on Pluto and on Saturn's giant moon Titan, one that researchers studying the data have openly said they simply cannot yet identify, and captured detailed new imagery of star-forming clouds and merging galaxies that continue to reshape how astronomers model the earliest chapters of the universe. None of that is slowing down. If anything, the pace of genuinely new, still unexplained findings coming out of this single telescope has accelerated as its instrument teams get better at squeezing precision out of hardware that has now been flying for the better part of half a decade. The Kreidberg team has explicitly said follow-up observations of LHS 3844b are already planned, aimed specifically at resolving the one question this study could not close on its own, whether that dark basalt surface is freshly formed rock, or an ancient one merely disguised by billions of years of exposure. And in a few weeks, an entirely separate but directly connected countdown reaches 0. On August 30th, 2026, at 7:26 in the morning Eastern Time, NASA's Nancy Grace Roman Space Telescope is scheduled to lift off from Launch Complex 39A at Kennedy Space Center aboard a SpaceX Falcon Heavy rocket, roughly 8 months ahead of its original target date. Roman carries a mirror the same size as Hubble's, but paired with a coronagraph designed to be at least 100 times more powerful than anything flying today. Sensitive enough, according to the mission's own projections, to directly detect planets around 1 billion times fainter than the stars they orbit. Where Webb spent years working up to reading the surface of one rocky world 49 light-years away, Roman is being built specifically to hunt for thousands of new worlds, using exactly this kind of direct imaging technique, at a scale no telescope in history has attempted. This is not a hopeful projection. It is a rocket already stacked, a telescope already sealed inside its payload fairing, a specific morning, 3 weeks from now, already written into the launch schedule. Now for the part that doesn't resolve as cleanly, because in the actual published science, it hasn't. The Kreidberg and Ziba team laid out two competing explanations for that dark basaltic surface, and as of publication, neither one has been ruled in or fully ruled out. The first is that LHS 3844b is geologically young, a world still shaped by recent volcanic resurfacing. Its basalt fresh enough that space weathering and micrometeorite impacts haven't yet had time to break it down. The problem, as the researchers themselves acknowledged, is that this explanation predicts detectable volcanic gases like sulfur dioxide, and Webb's instrument found none. The second explanation runs in almost the opposite direction. An old, quiet, geologically dead surface, its basaltic rock ground down and darkened over billions of years by relentless space weathering, the same slow process that has darkened the surfaces of our own Moon and Mercury. That version fits the missing gas signature far more comfortably, but it requires the kind of long-term geological silence that is difficult to confirm from a single set of eclipse measurements. Both scenarios remain genuinely on the table. The team was explicit that only additional, more targeted observations will be able to tell the two apart. Step back from this one planet for a moment, and a much larger pattern comes into focus, one that has quietly defined nearly every major leap in this field for the last 2 decades. Progress in exoplanet science almost never arrives as a single dramatic reveal. It arrives as a slow tightening of the question, one instrument generation at a time. Astronomers spent 30 years learning to detect planets they could never see directly, then spent another decade learning to photograph the easiest, brightest, most forgiving targets among them. And only this year, with a spacecraft that took a quarter century to design and build, did they manage to read the actual mineral content of a rocky world surface from 49 light years away. Each step made the next one possible, and each step also quietly retired an older assumption. The old model of the solar system as a uniquely rocky, uniquely water-bearing anomaly is not being demolished by any single headline. It is being worn down, planet by planet, spectrum by spectrum, by teams willing to spend years chasing a signal that starts out 10,000 times fainter than the noise around it. What most people, scrolling past a first-ever image headline, never see is that the actual first is almost always smaller, quieter, and considerably harder one than the version that goes viral, and also, in nearly every case, considerably more important. Consider what that means for how these stories get told at all. A viral headline needs a single dramatic image, a single clean moment, something a thumbnail can capture in half a second of scrolling. Real astronomy almost never hands anyone that. It hands them a graph, a spectrum, a curve, a scatter of data points collected across 3 separate eclipses 2 years apart, and asks them to trust that the graph means something enormous. LHS 3844b will likely never have a striking photograph of its own because there isn't one to take. Even Webb's most powerful instruments can't resolve a disk that small at that distance into anything more than a single unresolved point of light. The actual discovery lives entirely inside a chart of brightness against wavelength, decoded by people trained for years to read exactly that kind of chart. That gap between what a discovery actually looks like and what a headline needs it to look like is where nearly all of this genre's misinformation is born, not out of malice, but out of the simple fact that a spectrum doesn't get clicks the way a picture does. There is an image, still circulating from September 2022, of a faint, slightly asymmetrical blob of light sitting beside a small white star marker on a black background. Webb's first real exoplanet photograph, HIP 65426b, unremarkable to look at, genuinely historic in what it proved was possible. Nobody who saw that image at the time could have told you, just by looking, that within 4 years, the same telescope would be reading the mineral composition of a much smaller, much colder, much harder world using nothing but the faint heat leaking off its sunlit face. That is the part of this story worth sitting with after the numbers fade. Somewhere out past the constellation, the red dwarf LHS 3844 sits in. There's a planet with one face locked eternally toward blistering daylight and one locked eternally into cold and dark. A world no human eye will ever see directly, no footprint will ever cross. And yet, for a few careful hours, spread across 2 years, a piece of human engineering 90 million miles from Earth managed to read what that world is actually made of, the way you might recognize a stone by its color without ever touching it. Somewhere on that permanently sunlit hemisphere, basalt that may have hardened before complex life ever existed on Earth is still radiating heat outward into the dark, indifferent to whether anyone is watching, indifferent to the headlines being written about it 49 light years away. It has been doing that for longer than our species has existed, and it will keep doing it long after this video, this channel, and everyone reading these words has gone quiet. The only thing that changed this year is that, for a few precious hours, something built by human hands was finally close enough, sensitive enough, and patient enough to notice. So here is everything in one breath. Webb's real first direct image of an exoplanet happened back on September 1st, 2022. with the gas giant HIP 65426b. Not this year, and not the viral claim currently circulating online. What did happen this year, published May 4th, 2026, was something new entirely. The first direct determination of a rocky exoplanet's surface composition on a scorching, airless super-Earth called LHS 3844b, revealing a dark basaltic world that resembles the Moon or Mercury far more than it resembles our own planet. Getting there took 3 separate eclipse observations across 2023 and 2024, a search for volcanic gas that came back empty, and a conclusion that still splits into 2 competing explanations. Nobody has fully settled. In 3 weeks, on August 30th, 2026, the Roman Space Telescope launches to hunt for thousands more worlds using this same direct imaging approach, at a scale no mission before it has attempted. If you want to know what Roman finds once it's finally in space, and whether follow-up observations ever settle what LHS 3844b's surface actually is, subscribe and turn notifications on, because I'll be covering both the moment there's something real to report. Here's an easy one before you go. Would you rather know exactly what a distant planet's rock is made of, or exactly whether it has an atmosphere at all? Which mystery would you chase first? Tell me in the comments. I read every single one.